Hey everyone, so today's class, this is a bit of extension work leading up to the holiday weekend. There's nothing for you to turn in. You do have to be familiar with a few things from this class though, whether you turn it in or not. I do expect you all to look through it, all right? But there's no due date, so do it on your own time when you have a few free minutes. So we're going to talk about the Millikan oil drop experiment. You may have heard about it back in your chemistry classes. We're going to talk about Millikan's findings, what the point of his experiment was, and we're going to do some of the math that he did when he actually did his experiment. So before you do anything else, watch the video right here. I'll hopefully remember to put a link in the description next time. You can always just copy over that URL though. And that'll describe it, all right? So after you watch that video, it's only like a minute long, then come to the rest of this. So a few things we just have to remind ourselves about electric fields. Let's see. So what do we know about the strength of electric fields between two charged plates? It's the same strength everywhere, right? So between those two plates is the same strength at all points. Between plates. All right, so as the video kind of described, Millikan put these charged oil droplets between two plates. How did he charge them? I think he shot like X-rays at them to give them charges, okay? And the two plates, one was positive, one was negative. He created a voltage. That created an electric field between the two plates. So the oil drop felt an electrostatic charge pulling it upward, which is just Q times the strength of the electric field. And of course, it felt gravity pulling it downward. So Millikan played around with the voltage, and therefore the electric field, changing it, making it stronger voltage, stronger electric field, less voltage, less electric field, until the oil droplets started falling at constant velocity. Okay, a lot of people think that the oil droplets were suspended. Sometimes they were motionless, but constant velocity was the important thing. Because if objects have a constant velocity, we know that the acceleration equals what? 0. Therefore, the net force equals 0. Therefore, we can keep going with this, the electrostatic force would be equal to the force of gravity. Therefore, Q times the electric field equals mg. Now, Millikan was able to figure out what E was because he knew the voltage and the distance between the plates. He knew what M was by looking at the size of the oil drop. And of course, he knew what little g was, so he was able to find Q. And he found that those Q values were always multiples of 1.6 times 10 to the negative 19 coulombs. Sometimes he got, let me just fix that 9. Sometimes he got 1.6, sometimes he got 3.2, 4.8, and so on. But always a multiple of 1.6 times 10 to the negative 19 coulombs. So he concluded that that charge must be the charge of an electron. And a proton, for that matter. Because at that point we kind of knew they were equal. So we're going to look a little bit at what he did. This is a bit burdensome of a question. There's a lot of steps, but it's actually really not that bad. You just have to do it piece by piece. So it says an oil drop with a radius of, it's pretty exact there because I want you to not to round here. So this is the radius of the oil droplet. R equals 7.44257 times 10 to the negative 7 meters. So he could tell how big the oil drop was. Falls at a constant velocity. Okay, so good. So we know that Fe is going to be equal to Fg between two charged plates. The electric field strength between the two plates, E, is equal to 18,750 newtons per coulomb. What is the charge on the oil drop? So we're looking for Q. And, we're getting another piece of information here. The density of oil. So in physics, we use rho for density. It looks like a P. We use rho. You can write it D if you want. 886 kilograms per meter squared. Meter cubed, actually. Okay. So we established earlier, and we spoke about why, since it's falling at constant velocity, we know that the force of gravity pulling the oil drop down has to be equal to the electrostatic force that's kind of helping it levitate. So near Earth's surface, Fg is equal to mg, and Fe is equal to Q times E. Okay, we did that formula last time, if you recall. Actually, let me write it up here. Last time we learned that electric field is Fe over Q. If we cross multiply, Fe equals E times Q. But anyway, so we know E, we know G, but we don't know Q. That's what we're looking for. We don't know M either, but how could we get M? How could we get the mass of this oil drop? Well, we know the radius of the oil drop. We know the density of the oil drop, so can't we get the mass? So you probably did this back in chemistry. This is not something you really need to know how to do for a physics class, but I think it's a really good skill to have and one that you should just know going forward. So you should know that mass equals density times volume. I don't know how it was written exactly in chemistry class. It would probably look more like this in chemistry class, actually. Density, they probably wrote the word density, equals mass over volume. That's probably how they wrote it in chemistry. Well, we know the density, 886. It's important to use the units here, kilograms per meter cubed, equals the mass, that's what we want, over our volume. Well, volume of a sphere, right, because it's an oil droplet, is 4/3 pi r cubed. Well, what's r? We're given r. 7.44257 times 10 to the negative 7 meters cubed. All right, looks like a lot. It looks really burdensome, but all you have to do here is cross multiply. So basically, all you have to do is 886 times 4/3 times pi times, and then I would put this in parentheses, 7.44257 times 10 to the negative 7 cubed. All right, and I get a mass of exactly, in this case, 1.53 times 10 to the negative 15 kilograms. All right, so we just got the mass. That's not our answer, but we needed to find the mass to do the next part. So now let's plug everything in and solve for Q. So mass, I just did that. Mass is 1.53 times 10 to the negative 15. All right, I'm going to leave the units out for now. G is 9.8. Q is our unknown. And the electric field strength is 18750. Okay? So solve for Q, you have to divide both sides by 18750. So let's do that. And you should get, and there might be a little bit of rounding you have to do here, but you should get 7.99679 times 10 to the negative 19 coulombs. Now you might be saying, do I need all those significant digits? Yeah, just hold on to them for now. They'll come in handy in a second. So number 8 says, how many excess electrons are on the oil drop? I should have mentioned that the top plate, if I'm not mistaken, I think the top plate was positive and the bottom plate was negative. So we know that I had to have an excess negative charge. I could be wrong there, but anyway, how many excess electrons are on the oil drop? You probably won't get a perfect whole number, but you should be very close. By the way, if you're kind of getting hung up on the negative or positive, I don't think it matters. It really doesn't matter that much. All that matters is the amount of excess charge. I mean, you could tell if it's positive or negative by the charge of the top plate. If the top plate is positive, then the charge has to be negative on the oil drop, right? Because it's attracted to the top plate and repelled from the bottom. If the top plate's negative, then the charge has to be positive because it's being pulled up to the top plate, all right? But I wouldn't get hung up on that. Most questions ask you for the magnitude of the charge anyway. So how many excess electrons are on the oil drop? You could also say how many excess elementary charges, they might say. Elementary charges. That way it's not positive or negative, it's just elementary charges are on the oil drop. So you take that charge from before, this number here, copy, paste, and you divide by the charge of an electron. Actually, we'll do it the right way. You multiply by one elementary charge is 1.6 times 10 to the negative 19 coulombs. Multiply it through, and you're going to get a number really close to 5, you're going to get 4.998. So that's how many electrons you have. Now, some people might be saying, well, that's wrong. It has to be a whole number. Well, there's a little bit of rounding in here and so on. So just realize that, you know, it is basically 5. If you got like 4.7, then yeah, it's not quite right. But if you're getting like 4.9, 4.95, something like that, then that's good enough to say, you know, due to rounding, we could say pretty, you know, pretty confidently that that's 5 electrons. All right. So that's basically what Millikan did. And when Millikan did this, all the different sized oil drops had different charges. If a big oil droplet, okay, so if you had a really big oil droplet falling with constant velocity, there's a greater force of gravity acting on it. So there had to be a greater electrostatic force acting on it. So it had more charge. The smaller oil drops, when they were falling with constant velocity, they had a smaller force of gravity acting on them. So they needed a smaller electrostatic force to hold them up. So in those cases, they had less charge.